Now, the harder problem is to go backwards. Realistically, as a chemist, we make things in lab all the time, and we need to get confirmation that we made what we meant to make. There's all sorts of tests we can run, spectroscopy and spectrometry, and oh my mercy, we can do all the things. One really cool thing is just simply called elemental analysis. You take your compound, you basically heat the bejeebies out of it, and it goes through a few detectors that are very specific on what they're looking for and allows us to get back information that is mass percent. So in that situation, you're going the opposite direction. So this sort of problem you don't know the formula at all, and it would say, what is the molecular formula? Now I'm going to go for molecular formula. I'm doing the harder version of the problem, and I'll show you where you would stop for the easier version shortly. Of a compound with a molar mass equal to 110.12. So I'm going to use the same example. I'm just going to show you how it works backwards. Grams per mole. That is, so this is where you would be given these percentage. 65.44% carbon, 5.50% hydrogen, and sometimes they'll give you the percent oxygen, and other times they'll be tricky, and they'll say with the remainder being due to oxygen. When it's tricky, don't let it be tricky. You know that all the percentages have to add up to 100. So you would take this right here, and that is 70.94. So 100% minus the 70.94% is going to give you the 29.06% that is due to oxygen. So now you have your 3% for your 3 elements in your compound. So what you want to do is take those 3 and write them as mass values, because again, this is mass percent. So what you can do is that 65.44, we're going to take that and we're going to rewrite it as 65.44, and we're just going to put a gram behind it. Because what you're saying is for every 100 grams of the compound, 65.44 grams is due to carbon. 5.50 grams is due to hydrogen. 29.06 grams is due to oxygen. So if we write it that way, then it's going to set us up to get to a mole ratio, which is what you actually need to do the formula. Because remember, a formula is a counting ratio, and we count in moles. So your job, go to moles, which is your job often in this class. So grams to moles for carbon. Look at the periodic table. You'll find that 12.01 grams of carbon is what you have a mole of carbon. We have 65.44. So when we do that math, we're going to find that that's actually equivalent to 5.449. I'm just going to use some extra sig figs for a while. Well, technically I have 4 right now anyway. Moles of carbon. Now keep going. This is where you might want to speed up. For the hydrogen, 5.50 grams at 1.01 grams of hydrogen for every 1 mole of hydrogen. Do that math, you get 5.45 moles hydrogen. One more step. Well, one more time at this. 29.06 grams of oxygen. You guys use the 2 decimal place, so 16.00 grams of oxygen for every 1 mole of oxygen. If you do that math, you're going to get 1.8 0.816 moles of oxygen. All right, so that's a mole ratio. Technically, that is a counting ratio. We're not going to use those numbers as they are to write a formula because that would look hideous. You're going to take those, you're going to divide each one by the smallest, so one of them is set to the whole number of 1. So who is our smallest this week? That would be the 1.816. Divide everybody by that number. When you do so, you get clean numbers of 3 moles of carbon to 3 moles of hydrogen to 1 mole of oxygen. So now that you are at whole numbers, or extremely close, sometimes the math will get you very close and not a perfect whole number. It's got to be really close if it's a number we're giving you on a test or something. In real life, with research numbers, sure, it's going to be off a little bit. We might have to see what's up, but we're going to give you clean numbers. So C3H3O1. I'm going to write the 1 for sport right now just because I need you to look at that. So this is the simplest whole number ratio. This is what you should be able to get to just from the mass percent with nothing else. So this is that simpler type of problem. If it had said, what is the empirical formula? Instead of molecular formula, it could have said empirical. And in that situation, it doesn't need to give you the molar mass. If it just says empirical at that point, then you get to stop right here. However, we're doing the harder one. We're doing the molecular formula. So this is another type of problem that my students had on their first test, is if I give you the empirical and I give you the molar mass of the actual compound, you need to be able to tell me what the molecular formula is for the compound. So the way we're going to do that is we're going to say for the empirical versus the molecular. The idea is they're either the same, or so it's either multiplied by 1, as in the empirical is the molecular. It can't be simplified any further. The molecule's actual formula can't be simplified any further. So therefore, they're empirical, the simplest whole number, and the molecular are the same thing. Or it's multiplied by some whole number to get between them. So we need to figure out what that is. So the way we're going to do that is you're going to have the empirical formula, which we figured out was C3H3O. Now, add up that guy's molar mass. If you do that, you get 55.06 grams per mole. Well, we were given the molar mass of the molecular formula to be 110.12 grams per mole. Well, what do you have to multiply 55.06 by to get 110.12? Good job, times 2, right? So therefore, you just need to take the formulas because the same factor is going to relate to the formulas and therefore their mass. So C3H3O2 gets you to times 2, gets you to C6H6O2. Whoops, I said that wrong. C3H3O1 times 2, C6H6O2. And now you have that final answer it asked for originally. All right, so one more time. Mass percents are given in the problem, and it asks you for the formula. If it asks you for empirical, all you need is the mass percent, and you're going to do this part where you go from grams, using the periodic table, use their molar mass, and go to moles. And you're going to do that for each one of them. Your second step is going to be to divide through by whatever the smallest one is, so that you get at least one of them to a whole number. So that last one ended up being a 1 there. If you're at a whole number ratio at that point, awesome. Please make a note right now that you may need to multiply up at this point. Say you got 1 to 1.5 to 1.5. 1.5 is not close enough to a whole number. You need to multiply all of those by 2. So you would get 2 to 3 to 3. Just be ready that you may need to multiply it by 2 or by 3 or whatever in order to get an actual whole number ratio right here. So I did a problem that did not require for me to multiply up, but you may need to do that one more step to get that whole number ratio. Once you get the simplest whole number ratio, that's your empirical formula. If they ask you for an empirical formula, you're done. If in the problem it does actually give you the molar mass, then you're going to use the molar mass to find the molecular formula. And again, you can't go to molecular without it. All you can get to is the empirical. All right. If you have the molar mass, then you're just going to take the empirical formula you bothered to find. You're going to add up its molar mass. You're going to use the molar mass that we gave you in the problem and figure out that factor. Once you know the factor between the two molar masses, apply it to the empirical formula, and you'll have the molecular formula.